The first presentation by Andreas. It's about quantum ready or quantum risky post-quantum era for network operations. Welcome, Andrea, as a speaker.
Thank you, thank you. So, once again, I'm Andreas Polyrakis. Different hat this time. I'm Director of Strategy and Business Development at Digital Realty. And I will speak about this topic of quantum safe networking, quantum safe communications, if you prefer. Mostly from the point of view of an operator, and I will try to shed some light on this topic and explain why we need to start taking actions immediately, as soon as possible, if not immediately. So, in case you do not know Digital Realty, we're a leading global data center operator and co-location provider. We have more than 300 data centers around the world. We're very strong in Europe and EMEA. We're number one according to CloudScene. We're also very strong in Greece. Digital Realty has acquired Love the Helix, so we have 4 data centers now in Koropi, and we just launched another one at Iraklio in Crete. I do not see the animation working. Why is that? Any idea? Okay, in any case, this is the agenda for today. I spoiled the surprise is spoiled, but I will quickly speak about quantum computers, what they are and what is the status and maturity. I will speak about internet cryptography today, symmetric and asymmetric, and the role of entropy in the cryptography. And I will try to explain how the future computers, the future quantum computers, will break this cryptography. And actually, I will explain why the future computers break even the data that flows in on the internet today. I will elaborate on the 2 main categories of solutions, post-quantum cryptography and quantum key distribution and the hybrid solutions. I will speak about the readiness level and maturity and timelines, and I will briefly say a few things about our role as a global neutral data center operator in the post-quantum era. So let me start with a brief introduction on quantum computing. Obviously, I do not intend to go very, very deep. The animation is broken, but I'm sure that you do not want me to go into this complexity. Which I don't really understand fully, to be honest. But, first of all, let me say that the perception that quantum computers are fast computers is quite wrong, actually. This is not exactly the case. Let me explain. So with traditional computers, as you know, the data is represented with bits, zeros and ones, and the bits are always either 0 or 1. And then on them we perform some computations, and these computations are deterministic, which means that with the same input, we always get the same output. And of course, this property allows us to create applications and algorithms that we can trust and that are predictable, and this is the spine of all this IT revolution that is happening the past decades. Now, quantum computers are something completely different. So instead of bits here, we have the notion of qubits. And the qubits doesn't just have a value of 0 or 1. They actually have both states. This is called superposition. So if we have 4 qubits like the example here, these qubits at the same time, they contain all possible combinations between 0, 0, 0, 0 and 1, 1, 1, 1 binary, or 0 to 15. Only when we try to read those qubits, then the wave functions collapse, as is the terminology, the quantum terminology, and we get a single value there with some probability. But I need to highlight that it's not that there is a value there that we do not know which one until we measure. All the values are there. All the values are there. So when you do a computation there, which is called unitary transformations in the language of quantum computing, actually we can perform functions simultaneously on all the values on the qubit. So for every value x, we have a computational f of x that it is stored together with the initial value. And only when we try to read the output, then this will randomly select one of the outcomes, and this is what we will read. And this doesn't really sound very useful, but actually this is a probabilistic function, so there are actually some probabilities attached to each value, and we can actually, through this unitary transformation, we can also play with the probabilities. So eventually, although quantum computers are rather useless for most type of computations, there are some applications where we can find some algorithms where the meaningless results get a very, very low probability, practically they are eliminated, and only the meaningful results have a good probability of appearing. So, to summarize, with classical computers, we have the ability to do deterministic functions, deterministic computations, but if we want to do this on a bulk set of data, this is practically, we need to do it sequentially or use many computers to do this in parallel. With quantum computers, we do all the calculations on all data at the same time. For certain type of applications, we are able to take advantage of the existence of certain algorithms that can help us get some useful results. So with quantum computers, there is a very, very niche category of applications that can run here. Okay, it's not general purpose computers. Yet these niche category of applications includes cryptography, includes AI and machine learning, includes statistical analysis, include analysis of financial data, analysis of DNA, and many, many other very, very interesting applications. I miss my animations, but anyway, a few comments about where we stand today. Today, the implementations, there are quite in an infant stage. There are many, many restrictions. Quantum computers operate on very, very low temperatures, usually very, very close to 0 degrees Kelvin, absolute zero. And they are very sensitive to external factors like temperature, variations, fluctuations, electromagnetic noise, vibrations, etc. So eventually, it is very, very difficult to create a reliable quantum computer. As a result, we need hundreds or even thousands of physical qubits in order to compensate for the high error rates and to create a single logical qubit. As a result, the implementations today can only handle a handful of qubits in the order of magnitude of 10, which is a very, 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 very low number, of course. However, there are significant progress on this the past few years, and within the next 3 to 4 years, we expect that we will be able to have hundreds or even thousands of logical qubits in implementations of hundreds of thousands qubits. And for example, IonQ just announced that by 2030, they intend to have 40 to 80,000 logical qubits in a single implementation. So things are progressing very, very fast. Now, how this affect cryptography? Before answering this, let me go quickly on how internet cryptography works. There are two basic categories of algorithms: symmetric encryption and asymmetric encryption. So in symmetric encryption, we use the sender and the receiver use the same key to encrypt and decrypt the data. This is quite simple, straightforward, but we need somehow to ensure that we share the key in a secure manner. So either we need to travel physically and exchange the keys, which is the case for military applications, for example, or we need to make sure that an already secure channel exists in order to exchange this data. So what we often do, we just pick up the phone and speak with the other party and decide on a shared key. Is not exactly secure because the phone is not exactly a very secure communication. So this is the problem with symmetric encryption. So practically it can only be used to encrypt some pre-agreed channels. It is not good for ad hoc communications. For ad hoc communication, we have asymmetric encryption. I believe you are familiar with this. We have a private key that the receiver publishes, and the sender uses the public key to encrypt. The receiver uses his private key to decrypt. And the idea here is that by knowing the public key, you cannot guess the private key, because this requires very complex mathematical computations, which is factorizing a very, very big number, which is practically impossible to run with classical computers. This is very, very easy to set up. It's very commonly used in all ad hoc communications, including HTTPS, TSS, SSL, SSH, PGP, and many, many other applications. Let me also say that in those protocols, usually it is only the handshake which is asymmetric. Then the protocol once you have a secure channel, you can exchange keys and fall back to symmetric encryption, which is less computational intensive. A small parenthesis to talk a little bit about entropy. So entropy practically is the measure of unpredictability in randomness. And I guess you all know that it is very, very difficult to create truly random numbers with with our classical deterministic computer. So either we need to use specialized cards for this, or very sophisticated algorithms. And there has been some very, very big failures in the past. For example, you may remember the Debian OpenSL back in 2008, which led to, it reduced the key entropies to just 15 bits, and it could be brute forced in seconds. So it is very important when we have a source of randomness to make sure that it is really, or adequately at least, random. So let's speak about how quantum computers can break the encryption of the internet. When it comes to asymmetric encryption, there is an algorithm which is called the source algorithm that was invented in 1994 that can be used by quantum computers in order to factorize big numbers. So practically, we have a very easy way to break all asymmetric algorithms. Of course, these implementations do not exist today. We do not have computers with enough qubits. We need something like between 2,500 and 4,000 qubits to break the current the key lengths that are usually used on the internet today. But these, once scalable computers appear, the asymmetric algorithms will be at stake. The symmetric encryption, on the other hand, in principle, is not breakable by quantum computers. But the problem is that quantum computers can be used to brute force symmetric encryption, and practically it is the effectiveness of quantum computers is as if we were halving the length of the key, if we're cutting the length of the key in half. So for some algorithms like IS-128, this is significantly weakened. It is still not trivial to break, but it's significantly weakened. IS-256 and of course IS-512 are still considered safe. So longer keys are still considered safe. Let me also say that when it comes to entropy, quantum computers can also brute force entropy in a similar way. So Again, if we have poorly constructed keys, it is much, much easier to be broken through quantum computers. So NIST has recognized this and published a report back in 2016 recommending to replace all existing asymmetric algorithms and to use longer keys on the symmetric algorithms. So, I hope you understand the problem. How much time do we have? I hate that I do not have my animations, but when the source algorithm was invented in 1994, we predicted that the day that we would be able to break internet encryption would be somehow between 2045 and 2080. The report of NIST brought this window about 10 years earlier, 2035, and there was an analysis done by McKinsey 2 years ago that brought this window somewhere between 2027 and 2035. Actually, there are several independent researchers or experts that say that this day will be maybe before 2030. So we do not have too much time. We need to act. We still have some time, but this is not exactly true because there's another kind of attack that can be played even today, which is harvest now and decrypt later. So the traffic that flows on the internet today, you can harvest it now and you can decrypt it in a few years with a quantum computer. And many of the critical information that is critical today will be also valuable and critical in a few years. So there is a problem, and several companies have identified this. And governments. I will elaborate a bit later. How am I doing with time? Okay. So let's see what are the solutions. Let me start with entropy. Obviously, we need to make sure that the entropy is as secure as possible. Please update your cryptographic libraries. This is a very easy step usually. Consider use hardware entropy sources where appropriate if you have very critical data or applications, and monitor the quality of your random generators. And of course, at the end of the day, we need to apply the level of security that is required for our application to our random number generators as a general guideline. Now, with regard to asymmetric encryption, we can use what we call post-quantum cryptography. As I mentioned earlier, the asymmetric encryption, which is widely used, is potentially breakable by future quantum computers, and we need to replace the existing algorithms with ones that are not breakable, or at least there is no known way to be broken, both by classical and by quantum computers. There has been some work already on this. NIST has already identified, has some draft proposals for some replacement. You can see this on the black window on the left. And EU and HCI and other organizations, ISO, also analyzing with NIST, but also the industry. There are already some implementations of TLS that are being tested by Google, by Cloudflare, AWS, Microsoft, and a few more players. With regard to symmetric encryption, as I mentioned earlier, the symmetric encryption per se is not broken, but what we need to do is to make sure that we use sufficiently long keys, like IS 512. The problem here with symmetric encryption is how we exchange our keys. And a solution to this, again, comes from the quantum world. It is called quantum key distribution. So QKD is a method that uses quantum mechanics, quantum properties, in order to safely exchange keys. And what is the idea here is that you have photons that are quantumly entangled. You keep the one photon yourself. You send the other photon to the other party. The photons have, if someone in the middle intercepts those photons and tries to read their state, the state will collapse, which means that this is I don't want to go into the details of this, but this is something that it is detectable on the entangled photon that we keep, so we know that someone has violated the communication. If, on the other hand, the photon reaches the other end and is not intercepted, you know that the communication was safe, and you can use the keys that have been exchanged in this way. And this is the basic idea behind QKD. As you
change keys continually.
And change keys continually. I will go into this a bit later. So, of course, as you understand, this is a very high-end and very expensive hardware. There are some limitations. The distance cannot be more than 100 kilometers because we need to maintain some photonic properties. Usually, we require a dedicated dark fiber just for the exchange of the keys. But it is secured by the law of physics and is considered unbreakable. There are some solutions that look like QKD, but are not using photonic properties. They are using algorithms, so it is a sort of hybrid. Again, eventually, they create a secure layer to exchange keys that will be used by symmetric encryption. Here, I would really appreciate if I had the animations, but I'm trying to explain QKD. Let me try to use the laser. So we have two network devices that connect with a data link. The network device can be a firewall, a router, a switch, an optical device, or whatever. The data link can be a dark fiber, a wavelength, a tunnel, whatever. Again, this is typically encrypted with a protocol like IPsec or MACsec or OTNSec. But we want to make sure that the key exchange is upgraded to a safe way, that it is quantum safe way. So what we do here is that we install two quantum key distribution boxes, one near each device. And we also need a dedicated optical channel. Usually, this is, as I mentioned earlier, this is a dark fiber, but there are some research, some early products to use just a wavelength rather than a full dark fiber. And there are some distance limitations that, again, we're trying to push more and more. But eventually, these QKD are able to create secure keys and push those secure keys later to the network devices. The network devices implement either some proprietary APIs or something standard. It's called HC0014. This standard is implemented in the newer devices, so they can receive the keys that they get from the quantum key distribution boxes. And eventually, they use those keys to encrypt for the protocols that they implement, and encrypt the link with those traditional protocols that we have been using already. Now, in a more complex situation, there might be some boxes between QKD and the network devices that we call the key management systems, and this can help you either distribute keys towards multiple network devices that you may have on the same space, or for some non-point-to-point topologies, or in order to manage to extend the reach of QKD further than 80 kilometers, so some sort of key routing, etc. But this is more or less the concept with QKD. Summarizing the solutions, QKD is very, very secure, but it is complicated and expensive, so we expect to see this in certain applications that are very, very critical, and mostly to secure some backbone links. Some UKD alternatives, like digital UKD, that are not photonic but algorithmic, also exist. And then PQC, this can be implemented in hardware, but also in software. So in concept, it is possible to upgrade legacy systems with this as long as there's enough CPU to support this. So it is relatively easier. Of course, we're not absolutely sure that these will not be broken by classical or quantum computers, but it is a very good way to secure the existing ad hoc communication or layer 7, especially on layer 7. And of course, depending on each application, the security requirements, we might see different companies deploy different solutions, or maybe hybrid approaches, having QKD on their backbone and PQC on the application level, etc. Let me quickly, I do not want to go into the details of this slide, but I just want to mention that there are several governments, including, of course, US, EU, UK, and many, many more that have a path to secure the critical infrastructures. Most of them try to have all the critical operations secured by 2030, 2031, and everything else by around 2035. Similar, we see a lot of carriers having some pilots and deployments. I have this indicative list that I compiled with AI, so something might not be completely correct here, but as you can see, many carriers are working in the direction of securing their network and services. And of course, the big tech companies also are looking into this. How do we secure our cloud on-ramps? How to secure our enterprise security, our firewalls, browsers, etc., etc. I will not go into details. You can have a look at the slide later if you want. I have this here mostly for reference. And a few comments about our role in the post-quantum era. So the neutral and open data centers are crucial to the development of the internet, and they are the home of all those new technology. For us, it is very, very critical to make sure that in our ecosystem, our customers find all the options that are necessary for them. And of course, these quantum safe options is also something that we want to have within our data centers. So there are a few different things that we are doing here. First is that we're trying to host quantum computers and generally the quantum ecosystem. And actually, there is a recent announcement about a significant installation of a first quantum computer in New York City. I have the QR code here if you want to read more. But of course, we are interested in hosting third parties quantum safe solutions. Carriers or operators are welcome to deploy in our data centers. We have some communication and some internal systems ourselves, so of course we are looking on how we can harden those systems too. And last but not least, we have this global platform that we call Service Fabric, where service providers can provide their services to our customers globally, and we want to attract as many quantum safe options there as well. Either it could be secure transport or secure keys as a service or entropy as a service or anything else. So this is what we are doing in a nutshell. So key takeaways: it is not too early to start working on quantum safe. If you haven't done it already, please start. If you are doing this already, please talk to me. I would be very interested to know where you are in this journey. That was all. Barely on time.
Any questions for Andreas? No questions. So thank you, Andrea, again, and we're moving to the next presentation.